Okay, so in this second part of the lecture, we just recall what we saw before in the first part, that we got the solution of the wave equation with some boundary conditions and initial conditions of this form, with this sign here and this combination of cosine and sine, this depending on the second one depending on t, the first one depending on x. We have here how to compute the coefficients bn and dn, and what we used to find this solution was the separation of variable, the method of separation of variables. Okay, so let's try to use what we learned in the first part to in a particular example. Okay, so here we have a particular example of the wave equation. Here, this form before in the first part of the lecture was our c square, our positive constant c square. Here we have the interval 0, 1, so L is equal to 1. So here we are collecting the information. This 4 is our c square, so we have that the constant c is 2. This 1 here plays the role of L, so L is equal to 1. And we have f equal to this function 2x if x is belongs to the interval 0, 1/2, and 2 times 1 minus x if the x belongs to the interval 1/2, 1. Okay, so, and this is the graph of f in this interval 0, 1. And remember that if we can talk later about that, but if you remember for the last part of the first part of the lecture, at some point we wanted to have this function f. We wanted to have a Fourier series representation for this f involving only the function's signs. So later on, we will extend this function in an odd way, which maybe is not in that way, so maybe we don't add this information here. And once we extend this as an odd function in the interval -1, 1, then we make it periodically, and we can copy the graph outside the original interval. Okay, but let's talk later about that, and now just forget about that, and we go back to our wave equation with c equal to 2, because c squared is equal to 4, L is equal to 1, and we have this function f, and this 0 plays the role of xi, the xi that was before here. Okay, so for all what we did in the first part of the lecture, we know that the solution is given by this uxt, this form. But now, in our particular example, we know that L is equal to 1, C is equal to 2, so we replace this information here. And now, we also know how to compute these two guys, Bn and Dn, which were related to the sign expansion of f and g. Well, if we look at the g, it would be super easy because the function xi is equal to 0, so dn is equal to 0 for every n. So that is the easiest part of this computation of the coefficients. And then for bn, we have to solve this integral here. Okay, so let's do that. Using the information that the coefficients dn are equal to 0 for every n, we can also rewrite the solution u as this new guy with only the bn sine n pi x cosine 2n pi t. And now we know that bn has to be this integral here for each n. So we compute these coefficients bn to finally get the expression of the solution. Okay, so it's 2 times the integral from 0 to 1 of f times this sine, but our f, if you remember the definition, we have that f is equal to 2x between 0 and 1/2, and 1 minus x between 1/2 and 1. So that's why we split the integral in 2 pieces, because the f is defined in 2 pieces. So this is our first step. Okay, now these two can go outside the integral. That's why we have a 4 here. And same for these two. That's why we have a 4 there. And okay, now to solve this integral and also the other one, we will use integration by parts, which means that we call this, let's say, u1, this u2, and then we have the same b prime here. So if u1 is x, then u1 prime is 1. If u2 is 1 minus x, then u2 prime is minus 1. And if this is b prime, an antiderivative of this function is minus cosine n pi x over n pi. So using this information and the formula of integration by parts, we have for the first piece this minus x cosine n pi x over n pi, and we have to evaluate this between 1/2 and 0, plus, because in principle it's minus, but then with the minus that b has here, it turns in this plus, the integral from 0 to 1/2 of this new guy. Okay, here, if you put 1/2 here, then cosine of n pi over 2 is always 0 for every n. And then when we put 0 here, also here, we get 0. So this first part is 0. Okay, and now these constants can go here outside the integral. And we have to solve this integral here. An antiderivative of cosine n pi x is sine n pi x over n pi. That's why here we have a square instead of only this guy. And when we evaluate this between 1/2 and 0, what we get is this expression. But this expression has different values depending on if n is even or is odd. Okay, so for odd, when n is even, we have that this is equal to 0. And with when n is odd, this function jumps from 1 to minus 1 every time. So we have this expression here. You can check then that we have this identity. Okay, that was the first integral from 0 to 1/2 and using integration by parts. Then for the second one, from 1/2 1, we again are using integration by parts with this u2 and this b prime. So here we have u2 and the antiderivative of like b, the function b, evaluating between 1 and 1/2 minus this other function here. Okay, this first term again is 0 for other reasons. When we put 1 here, this is exactly 0, and then when we put 1/2, this guy is 0. And okay, now we need to solve this piece. An antiderivative is this function, and we have to evaluate this between 1 and 1/2. And what we get is again this expression depending on if n is odd or even. Okay. So going back to the coefficients Bn. Bn was 4 times the integral from 0 to 1/2 of this guy, plus 4 times the integral between 1/2 and 1 of this other guy, because this was part of f, the definition of f of x. And putting together all the information, we have 8 times this number. Okay, so that was the final step to find our solution uxt with so now we know, if we go back to the expression that maybe is a bit quite early, here this was the candidate that we found from the first part of the lecture, and we knew everything but the coefficients Bn and Dn. Using the initial conditions, we find first that Dn is equal to 0 for every n. That's why this piece was the only surviving. And then we found this Bn, computing these integrals here. We split the integral in 2 parts because f was defined in 2 pieces. And we had to use integration by parts, then one time for each integral. And then we get this expression of Bn. So putting that information in our previous candidate, we get this solution. Okay, so this was an example with an explicit constant c, an explicit L, an explicit f, and g. Okay. So far we used the method of separation of variables to solve the wave equation, but this method works in general to solve partial differential equations, and that's why we are going to see this other example, the one-dimensional heat equation. Okay, so the heat equation is given here, the derivative with respect to T of U, the first one equal to a positive constant, c squared, and the second derivative with respect to x of U on an interval 0L, positive time. We have these boundary conditions and this initial condition. We have only one initial condition, and it's related to we have only one derivative of t. Okay, so let's use the separation of variable method to find a solution for this partial differential equation with these boundary conditions and these initial conditions. So first step, separate variables in the partial differential equation and the boundary conditions, both. We start with the partial differential equation. Remember that we are now looking for a solution of this form, where we literally separate the variables. We have capital X of x, capital T of t. Okay, so we plug this candidate into the partial differential equation, meaning exactly this. X stays exactly the same, and we have the first derivative of t because it's the first part, this ut, and for the other part, c squared uxx, we have this part where t stays exactly the same, and we have the second derivative of x. As we did before, we literally separate the variables, so we put together all what we have for x, and we put together all what we have for t. And now the only possibility is that each of these guys is equal to a constant, the same constant, and that constant receives the name of separation constant. So what we have is this. the part of t has to be equal to k, and the part of x has to be equal to k, where k is a constant that we don't know yet and has this name, separation constant. Okay, so we can rewrite the ODEs, the ordinary differential equations that we got from here, and we have these two ordinary differential equations, one for t and one for x. So that was the first part of the first step, plugging the candidate, which was separating the variables, so capital X and capital T, in the partial differential equation. So the second part of the first step of the method of separation of variables is to also use the boundary conditions, so also separate the variables in the boundary conditions. So when we do that, we have these two boundary conditions. This one turns into this equality that we have here. And again, when we do this method, we are not in general, we are not interested in finding the trivial solution, the solution equal to 0. We know that 0 is a solution. We don't care about that solution. So we will ask this t function not to be 0. So what we get is this first boundary condition for capital X. Doing the same for this other boundary condition with L. Again, we don't want the trivial solution, so we get x of L equal to 0. Okay, so the second step of the separation of variables method was solve the ODEs, the separated ODEs that we found in the step 1. So these are the two ODEs that we just found. The one for x with boundary conditions and the one for t without boundary conditions. Just we only have the ODE. So if we need to solve the separating ODEs, we will start for the one that we have more information. So the one for x in this case, capital X. Okay, so it's what I just said. We start solving the ODE for x since we have more information, the boundary conditions. Remember, this constant k is any constant, so we will have these three cases again, positive, negative, or 0. Okay, so remember that if we are in the case where k is positive, we can rewrite k as mu squared with mu a positive constant. When we are in the case where k is negative, we can rewrite k as minus mu squared with mu positive. Okay, so here we did the case equal to 0, which in the first part was left as an exercise. What happens if k is equal to 0? Remember, the equation for x is here, is the second derivative of x minus blah blah blah. But if we set k equal to 0, it's only the second derivative of x equal to 0. That means, integrated 2 times, that x is this function, some constant a times x plus some other constant b. Okay, but we also have the boundary condition. So when we use the first boundary condition, which is setting this x equal to 0, we get b equal to 0. When we set the second boundary condition, when we use the second boundary condition, capital X of L equal to 0, what we get is AL equal to 0, so A is equal to 0. Then we just again arrive to the trivial solution, and we don't want that. So it's not that k equal to 0 is not possible, is that we won't care about this case because we don't want to find the trivial solution. We want non-trivial solutions. Okay, so k equal to 0 is done. Let's do the interesting ones, the positive and the negative. And here this blue comment is because we can recycle what we did in the first lecture. So we already know the solution of this problem. That's why maybe this part would be shorter. So recycle that information. We know that K positive also didn't work, and didn't work in the sense that gave again the trivial solution. So we know that the good case was K negative. So let's check the previous part of the lecture to see how we get to this case and how we get to this solution. It's just exactly the same equation, so we will arrive exactly to the same x, capital Xn, with this n pi over L. So we have for each n this possible value of mu, so for each n we have a possible k. And now this is different from the previous lecture, the previous part, the previous video, because the equation for t is different. Before, when we were working with the wave equation, the equation for t was a second order ODE. And now that we are working with the heat equation, the equation for t is a first order ODE. So we have a first order ODE with constant coefficients, so we can use also, if you want, the characteristic method, but this is quite easy because we can solve it by hand, let's say. So meaning what? So this was the equation for t with k. And now we put, maybe it is plus, I'm not sure if it's correct, let's check, otherwise we can change it now. No, so it was a minus, so let's change that. But then since we are in the case where k is minus mu square, I think this plus is correct and this minus is not correct. Sorry, 1 second. So where is the equation for t? Here. No, the minus is correct. So this minus is correct, and so this should be a minus. And now that, okay, so this was a minus, but now we know that k is negative, so we get this plus here and this value of mu. Okay, oops, I forgot to change here. Okay, so going back, we are in the second step of the separation of variable method, solving this heat equation. We already got the solution for the function x because we recycled what we did in the first part of the lecture, and now we are solving the equation for t, which is different from the first part because this one is a first order ODE. So we take our ODE. We now know the value of k because we found these values for every n. So we replace that information and we solve this ODE. And I was saying that we can solve this by hand, meaning that we just put this put this in the other side of the equation. Then what we have here is exactly the log of capital T, small t, the derivative of this function by the chain rule. And now we can integrate this identity. Then we have a constant here because we are integrating, and then we want to find t, so we apply the exponential here to get exactly this guy. And when we integrate from this line to this line, we also get this t and this constant. Okay, so, and we can use the properties of the exponential, and here we have a new constant, and we have this function here. So we will choose this constant equal to 1, and we just consider this function. even better, we get a solution Tn where we have here any constant that will vary with n. Now we are calling Bn, and this function that we found here. Okay, so finally we obtain for every n this solution Un. The first part of this exercise gave this sine n pi over Lx, and when we solved the equation, the ODE for t, we got this part. And now we know that the most general solution that we can suggest is any combination of these Un, and that's why this is our candidate. Where this Pn, we don't know this constant Bn. So far we know everything, but not this constant. Okay, so that was step 2. We solved the separated ODEs that we got from the first step, where we separated the variables in the partial differential equation and the boundary conditions. So, final step, using the initial conditions to find the Fourier series solution. Okay, so we evaluate this candidate at t equal to 0 and use the initial condition ux0 equal to f. So doing that, we get, this is also easy to compute because fortunately exponential to the power 0 is 1. So we get exactly this expression. And again, what I was trying to say at the beginning of this example, we have only f defined on the interval 0, L, but we know that for a function f defined on this interval, we can consider the odd extension in this other interval, minus LL, and we will get the half-range sine series expansion of f, which is exactly what we have here. So that means that we now know that these coefficients Bn are the sine coefficients of the half-range sine expansion of f. And we have a formula to compute them, which is exactly here. It's 2 over L of the integral from 0 to L of f times sine n pi over Lx dx. Here the p is L. Okay, so conclusion of this part. The solution of our heat equation in this interval 0L with positive time, with these boundary conditions and this initial condition ux0 equal to f is given by this guy, and we know exactly how to compute the coefficients Bn. Okay. So, can we solve the one-dimensional heat equation with non-homogeneous boundary conditions? So that's it, that we have here a T1 which is positive and a T2 which is positive. Instead of, if you remember here, the boundary conditions were equal to 0 for x equal to 0 and for x equal to L. So the question is, can we solve the one heat equation with non-homogeneous boundary conditions with also using the method of separations of variables? Okay, so the answer will be kind of yes, but we need a trick. So what's the trick? What do we have to do to be able to use the method of separation of variables to solve equation with non-homogeneous boundary conditions? Okay, let's see the trick. We consider this problem, which is exactly the heat equation, but removing all the t's. So if we look at the heat equation, here. If we remove the t's, we will get the second derivative of u0 equal to 0 and ul equal to 0. So we go back to our problem here, so to the trick. We think about this problem, which is kind of removing the t of the partial differential equation and the boundary condition, and we get this problem. When we solve this problem for t1 and t2 positive numbers, what we get is this function w. Look, when I put here 0, I get t1, and you can compute that when we set x equal to L, would kill this L, and then we will get the t2. And this function has a particular name. It's called the steady state solution of the problem. The steady state solution of our partial differential equation with the boundary conditions and the initial conditions. Okay, so we have this function, we have this steady state solution, and we will use it to reduce the heat equation with non-homogeneous boundary conditions to one with homogeneous conditions. How? We want to solve the heat equation with non-homogeneous boundary conditions, which means having here T1 and T2, positive numbers. So assume that we have a solution. We already know that U is the solution, uxt is the solution, and we will consider this extra problem, this auxiliary function, bxt equal to uxt minus the steady state solution. So this guy we just compute, the steady state solution of the associated partial differential equation. And now we wonder, which PDE does B verify? So we take B and we compute the derivative with respect to t of B, and what we get is exactly the derivative of u with respect to t. Since we know that u is the solution of the heat equation, we know this identity that we have here. This is equal to c squared, the second derivative with respect to x of u, and then if you compute that derivative, the derivative of b with respect to x 2 times, you get exactly this. Okay, so our function bxt verifies also the heat equation. And how about the boundary conditions? When we put x equal to 0, we have u0t minus t1, which is exactly 0. When we set x equal to L, we have u of L t, which is t2, and then this purple part, which was the steady state solution, also takes the value t2, so we have this 0. And finally, the initial condition bx of 0 would be equal to ux of 0 minus the steady state solution, which now has a name, wx. So the initial condition for b would be f of x minus w. So, summarizing, our auxiliary function bx of t, which was uxt minus this steady state solution of the original problem, solves this problem, the heat equation, this homogeneous boundary condition, and this initial condition, which is different from the one from u, is another function. But still, so we already know how to solve this problem because it's exactly what we were doing in the first part of the lecture and in the first part of this part of the video. So we know how to solve partial differential equation with homogeneous boundary conditions and any initial condition. So we apply the method of separation of variables to solve this auxiliary problem for B, and then we know that we can get U just adding the steady state solution. So from what we did before, we know that this is the solution. B has this form, and we know how to compute the coefficients. But now remember, this new initial condition is not exactly F. It's F minus the steady state solution. That's why we have this factor here. Now, recalling that our B is exactly U minus the steady state solution W, we find the solution of the heat equation with non-homogeneous boundary conditions, which were these T1 and T2, just with B, that we find this B through the method of the separation of variables with homogeneous boundary conditions, and this adding this steady state solution, which is looking at our partial differential equation and solve the ODE, removing all the T's. So if we go back to our question, can we solve the heat equation with non-homogeneous boundary conditions using the method of separation of variables? The answer is yes, but we have to do this trick of, okay, I first compute this guy, which is the steady state solution associated to the partial differential equation, and then I solve an auxiliary problem for B, which has homogeneous boundary conditions, and another initial condition which is related to the function f, that was the initial condition of U, minus the steady state solution W. And we know how to compute the coefficients, which now here we don't have only f because of this trick of trying to reduce the non-homogeneous boundary conditions to homogeneous one. So now we have this f of x minus this wx, where w is exactly this guy here, this function that only depends on x. So again, this same idea of recycling what we know. So the whole lecture, the lecture 5, was about the method of separation of variables. So the first step of this method was suggesting a candidate where we have product of functions with only one variable, depending on one variable each. When we plug this candidate into the partial differential equation, what we get is a couple of ODEs, ordinary differential equations. So we are recycling our knowledge of, okay, we have to solve a partial differential equation, and I reduce this problem to solve some ordinary differential equation because we already know how to do that. And then in this last part of the lecture, what we saw and what we learned in the first part was solving partial differential equations with homogeneous boundary conditions. Now, if I have non-homogeneous boundary conditions, what I have to do is this trick of, okay, I just compute this auxiliary function, this steady state solution, subtract this function in some sense, and reduce the problem of non-homogeneous boundary conditions to one with homogeneous conditions. So this idea of recycle what we learned is all the time there. Okay, so one example, and I think we are done with this lecture. We have here the heat equation with non-homogeneous boundary condition, well, one is 0, but the other one is 100, so it's T1 is 0 and T2 is 100. And here the constant is 1. The L is pi. As I just said, T1 is 0, T2 is 100. And the function f is also 100. Okay, so the steady state solution here, we just saw, is this guy, T2 minus T1 over L times x plus T1. So replacing the information that we have here, W is 100 over pi times x. I don't know what happened here, but let me correct this. The solution. Okay, so the solution uxt is given by, as we said, the steady state solution of the problem plus this this bx of t, where we know how to compute these coefficients. That now the difference within the homogeneous conditions is that the function that we have here is not f, is f minus this steady state solution, which in this case is this one, 100 over pi x. So again, we can integrate this by parts. The computations are not here. Let's leave it as an exercise. And we would get 200 over m pi. So finally, our solution uxt is given by 100 over pi x plus this guy, where we now know the coefficients. Okay, and so remember that this the form of the solution ux we know because we have this conclusion here. But when we don't know this particular form of ux, each time I have to solve a partial differential equation, I would use the method of separation of variables, following these 3 steps that we were doing for the wave equation and for the heat equation. So in the case I have homogeneous boundary conditions, I can directly apply the method of separation of variables, which consists in these 3 steps, plugging the candidate into the partial differential equation and the boundary conditions as the first step. Second step, solving the ordinary differential equations, the separated ordinary differential equations that we got in the first step. And third and final step, using the initial conditions to finally determine the coefficients of relating to some Fourier series of the initial data. And those are the 3 main steps of the separation of variable method. Then, when I don't have homogeneous boundary conditions, I can use this trick where I have to compute separately the steady state solution associated to the problem, and then this other function that we were calling bxt, and this function will verify the same partial differential equation but with boundary conditions, homogeneous boundary conditions. And the initial condition for the function b will be the original f that u has as the initial condition minus the steady state solution. And this is the trick that we have to solve non-homogeneous partial differential equations with non-homogeneous boundary conditions. Okay, and that is for today.